Okay, so yesterday we just looked at, sorry, Monday, on Monday, we looked at thermodynamic cycles in general and then how they work, how refrigeration would be, heat engines and heat pumps and all those things, right? And then today we want to specifically consider what we call gas cycles. Okay, so these are just the things you should be able to get at the end of today's lecture to understand the different ways cycles are classified, evaluate the performance of gas power cycles, develop simplifying assumptions, review operations of reciprocating engines, analyze both closed and open power cycles, and then at the end of the day, the main thing is to solve problems based on the Otto, the diesel, and then the Brayton cycle. So I'll take my time to just give us an understanding of what the gas cycles are about, the different kinds of cycles that they are, and then what these particular cycles are going to be, and how we do the calculations on these cycles. So that if you come across any question on an Otto cycle, a diesel cycle, or a Brayton cycle, you know how to go about it. So, see, at a point, focus was given to working with fuels to produce some kind of work. And there's an amount of heat that can be generated when different fuels are burnt. And that heat that is generated, we can use it with a working fluid to produce the work. So maybe I have a system, I burn a certain fuel, right? It generates some amount of heat, and then that heat is transferred to a working fluid. We talked about the working fluid the last time, that it is the fluid that can receive heat or can give off heat, right, in our thermodynamic cycles. Okay, and these ones they work with thermodynamic cycles, so there's going to be some compression, some heating, some cooling and expansion. So that's what this slide is just talking about. The fact that there is a way we can heat fuels, or we can burn fuels, or utilize fuels, obtain heat from the fuels, transfer that heat to a working fluid, and then use that in generating power or generating some kind of work, right? So that's what this particular slide is talking about. And here we are being asked, what is the best way to convert heat to power? I'm saying that the decisions that have to be taken by an engineer include deciding the nature of the working fluid. So if the fluid will exist as a liquid at some point and a gas at another point, then this is called a vapor cycle. Or whether it remains as a gas at every point, then that would be a gas cycle. So in order to design system that will be able to convert heat to power, heat from the fuel to power, right? Engineers need to consider the type of working fluid. Is it going to be the kind of fluid that would be a liquid at a point and become a vapor at a point, or is it going to be the kind of fluid that's going to be a gas throughout, right? If it's going to be liquid at a point and vapor at a point, that's what we call the vapor cycle, right? And then if it's going to be gas at every point, that's what we call the gas cycle. So for today, we are going to focus more on the gas cycles. And another thing that you also need to consider the kinds of reactions that will lead to the release of the fuel, right? And whether this is going to be within the engine. So that's what we call an internal combustion engine, or outside the engine, so an external combustion engine, right? So these things are important because it helps you know the kind of equations you would use for your calculation. So if we talk about an internal combustion engine, what we are just trying to say is that the fuel that is going to be used for the heating is inside the engine, or it's with the working fluid, right? And in the case of an external combustion engine, the fuel that will be doing the heating is outside, is outside the engine, or it's outside where the working fluid is, right? And then another thing that engineers need to consider is whether they are going to use what we call a reciprocating engine, or a system that works with a turbine, a compressor, a heater and a cooler. So the turbine, compressor, heater, cooler units, we looked at that when we looked at the thermodynamic cycles, right? Something like a refrigeration system. We have a point so that the refrigerant is going to absorb heat from the fridge. So that's going to be the part where it evaporates, right? That will be a heater part. Then we pump it and then we increase the pressure. So that's going to be the compressor part. Then we release this heat to the environment. So that will be the cooler part. It condenses and we compress it in. Sorry, we drop the pressure again. That will be the turbine, or something of that sort, something like a turbine part. Right, so just the thermodynamic cycles we've already looked at consist of these kinds of units. What we are saying is that we can also have what we call a reciprocating engine. So for that one, we saw it in, I think, lecture 3. It's a kind of engine that just has a rotating shaft, right? that keeps moving up and down to do some kind of compression and expansion. So we would see it as we progress. Okay, so we are being asked once again, what's the best way to convert heat to power? Choosing the best way to go can be a bit challenging. Um, okay, so what we are saying is that trying to determine the best way to convert heat to power can be a very complex thing, right? And remember, we said there's internal combustion and then external combustion. So we are saying that here internal combustion is going to retain more heat than external combustion, and that makes sense because let's imagine that I have my system this way. I have maybe my sorry, let me try this again. Keep forgetting this is in PowerPoint. Okay, so let's say I have an engine this way, right? And then I have my working fluid within the engine. If I should do my compression, my heating, and everything within the engine, right? I'm not going to have any case where the heat would have to necessarily move through a medium before it gets to my working fluid. But if it was an external case and I had my working fluid in here and then my fuel source out here, whatever heat is generated here, I would have to also ensure that that heat moves through this medium before it gets into the working fluid. So in that case, for internal combustion systems, it's able to keep more heat as compared to the external because now there's supposed to be another medium before heat gets transferred to the working fluid, right? So internal combustion engines are able to retain more heat than the external combustion engines. And for internal combustion engines, because we are dealing with a fuel that needs to be burnt, we also need to include air and oxygen within our system. So that's what's going to be our working fluid. And then the thing about this is that if we should do this right, there can be some kind of um reactions happening because I'm having air and fuel in my system. I'm adding yes, I'm having air in my system. I add a fuel and then I now compress and burn. Definitely, because of that burning process, there would be some kind of reaction happening that would change the composition. So it means I need to keep changing the working fluid. So that's what this point is just trying to say, right? So if it's an internal system, I have my fuel here, I have my air here, they react and form something else. So let's say carbon dioxide or whatever it is, right? And it's not carbon dioxide that I'm interested in. So it means that at a point I'll need to feed in more fuel, I'll need to feed in more air. Unlike the case where it is external, usually whatever fluid is inside, I can keep it inside for a very long time, right? So that's just the advantages and disadvantages we see. Another issue is that the fuels can exist in different forms. So we can have solid fuels, liquid fuels, and gas fuels, and they don't all bend to the same degree, right? So if you are having a system, you need to be very particular about the kind of fuel source you are using. If you are going to burn a solid, you know that you are going to end up having particulate matter being formed, and that might not be suitable if you are dealing with an internal combustion engine. So you need to know the kind of system you are dealing with and the kind of fuel that would be convenient for that kind of system, right? And then other factors that we consider are things like the weight of the engine, right? That would affect um, what we want to do. If the engine is going to be too heavy, right, then it means that we can't use it for certain applications. And if it's too light, it might not be able to generate enough power for certain applications. Okay, so we have different sources of fuels here. We have coal, we have biomass, we have petrol, diesel, kerosene. These are just examples, and we have their high heating values over here, right? I think we have their high heating values over here, then their phases, then the types of cycles that they work in, right? And then their classification. So whether it's going to be a gas or vapor cycle, whether it's going to be an internal or an external combustion engine, right? So these are just some examples. And is there a question? Okay, sure. Okay, so now let's go back to gas cycles. We're saying that in this lecture we are going to discuss the creation of gas cycles. Remember, we said for a gas cycle, the the source we are using or the working fluid we are using is going to be a gas at every point. So we're not going to have a case where it becomes a liquid at a point. So it's going to be a gas at every point. And for us, we are particularly interested in the Otto, the diesel, and then the Brayton cycle, right? So these three, in addition to being gas cycles, they are also internal combustion engines. So we'll see that very soon that these three are internal combustion engines, they are not external. So it means the fuel is within the system, or within the engine, or within the cycle, right? It's not outside and then the heat is being brought inside. Now, for Otto and diesel cycles, they are reciprocating engines. For the Brayton cycle, it's more of the turbine compressor heater cooler unit kind of thing, right? So let me just quickly show what I'm talking about for that. For the Brayton cycle, this is how it looks like, right? So we have a compressor part, we have a combustion chamber, so that's going to be a heating part, we have a turbine part, and then we even have the cases where we consider a cooling part, where we are removing the exhaust heat, right? Then we can have the Otto and then the diesel cycles. So for those ones, they are going to be working with, okay, I think I have an image for that. I'll show that one later, but they are going to be working with these kind of systems, so a reciprocating engine, right? So it doesn't have the compressor, cooler, and all those things. It just has a reciprocating engine, so the shaft here moves up and down. So that's why it's called reciprocating, right? And then it compresses and expands the fuel or our fluid. Okay. Yes. So these engines, they differ from other cycles because the process occur within the reciprocating piston cylinder arrangement and not an interconnected series of different equipment. So that's what we just said. The reason why they are um, reciprocating is because they are not working with other units connected together like a compressor, heater, cooler, and turbine system, right? And this would greatly reduce the weight of this heat engine. So imagine you have something like the Brayton cycle where you need a part for compression, you need a part for heating, you need a part for expanding your fluid, and you need a part for removing heat. That system is going to have a higher weight than if you have just um, one reciprocating engine, right? So that's the advantage of the reciprocating engine. It reduces the weight of the engine, so it makes it suitable for usually smaller applications like with our automobiles or our cars, right? And in jets and ships. So there are two principal types of the reciprocating engine. We have the, okay, I think there's a question. Okay, Maxwell, I think I'll get back to you. Okay, let me a minute. So all we are saying is that for the reciprocating engines, we have two types, right? We have the um, spark ignition engine, and then we have the compression ignition engine. So let me just give a little overview. So what we've said so far is we have gas and vapor cycles, but the ones we are considering today are gas cycles. The fluid is going to be a gas at every point in time, right? Then aside that, we said we have the reciprocating engine, and then we have the one that is a turbine compressor cooler heater unit. But we are focusing first on the reciprocating engines. Now, under the reciprocating engines, we have two types: spark ignition and then compression ignition. So when we are dealing with a spark ignition engine, right, we have a mixture of fuel and air, and then that gets ignited by a spark plug. Right, so there's a certain spark that is released and then it ignites our mixture. But for a compression ignition engine, we just compress air to a very high pressure, right? Inject the fuel into it. So please take note of this point because it will help us understand something later. We inject the fuel in afterwards because we get to a point where we start seeing enthalpy coming in, right? And enthalpy is going to come in because some material is going to flow in. The material flow in is the fuel that is injected. So please take note of that, right? So for compression, we compress the air and then we inject fuel into it. And when we do that, it auto ignites, so we don't need to add a spark. It would burn on its own, right? We are saying that spark ignition engines, they have advantages for applications requiring power up to 225 kilowatts. So if you're dealing with a system that doesn't require power above 225 kilowatts, you can just work with the um, spark ignition engine, right? And the thing is that for the yes, and for the spark ignition engine, because you don't have to compress it to the point where it would burn on its own, usually works with lower pressure, so they are lighter than the compression ignition engines, right? But then if you want to work with compression ignition engines, because you need to compress it to a point where the fuel can now burn on its own, then it means that you need to ensure that your vessel walls are thick enough to withstand that high pressure, right? And then they are used usually for more heavy duty applications. So they are used normally for applications where we need large amounts of power, so like heavy trucks, buses, right? These kinds of things. Okay, so this is just a little overview on the kinds of reciprocating engines and when we use one and when we use the other in reality. right? So this is just how the reciprocating engine looks like. I think if you should check the PowerPoint for lecture 3, this is in the animated form, so you can actually see the movements of the pistons up and down, right? And then these are just the parts of that kind of engine. Okay, now um you can see that when we come to some of these systems, they are a bit complex when it comes to analyzing them. So they're a bit complex when it comes to analyzing them, and this is because there are a lot of effects that we need to consider. So things like friction, right, and then the absence of enough time for equilibrium to be established during the cycle. So it makes it very difficult to um, properly analyze the system. So what we do is that we just make some assumptions, and then we take some things to be ideal cases so that we can do our calculations on them, and then later on we can now add in the complexities, right? So what you're just trying to say is it's the same thing we do with almost everything we do in engineering courses. We just take a complex system, we make some assumptions, we have an ideal form of the system. When we get our equations working, then we now start building up by including all the complexities and all the um, irreversibilities and all those things into our system. Okay, so the assumptions that we are working with are: the cycle does not involve any friction. So the working fluid won't experience any pressure drop as it flows in the pipes. Remember when we're doing fluid transport that if there's any kind of friction, right, it has a certain relation to the pressure drop. So we are just assuming that there's no friction in our cycle, so there's not going to be any pressure drop. And that point is also important. So unless the question states otherwise, we just assume that there is no pressure drop in our system. We also assume that the expansion and compression processes take place in a quasi-equilibrium manner. This means that they're happening very slowly, so they can approximate an ideal case. If they're happening very fast, we can't use ideal approximations for their analysis. So we assume that they're happening in a very slow manner so that we can work with ideal approximations. And another assumption is that the pipes that connect the various components are well insulated. So there's no heat transfer or significant heat transfer through them. So there's a point where we have heat being added to our system and removed from our system. Those are the only parts that we assume heat is being removed. But at every other location, we assume that heat is not being removed. Once again, that's also going to be a very important point, because when we start looking at the different cycles, Otto, diesel, and Brayton, realize that you will see graphs like this, and you see something like this with Q in and then Q out, and then this side here is going to be as maybe a constant entropy. So from point 1 to point 2, there is no heat that will be lost there, right? So we are assuming it's an adiabatic position. Okay, and then as time goes on, after we do the ideal approximations, we can now relax some of these assumptions and include the complexities in there. Okay, so before I continue, are there any questions up to this point? Before I continue, are there any questions up to this point? So we have what we call an open cycle. Now the thing about the reciprocating engine is that it is an open cycle, so yeah, it allows heat to leave with the exhaust gas. I'll explain what that means. Okay, so it's not truly a thermodynamic cycle which is restored to the initial state. So remember we said that if we have a cycle, ideally if we have a cycle, so let's say we have a case like this, we have point 1, point 2, point 3, and point 4. If it's a cycle, it means after I move from 1 to 2, 2 to 3, 3 to 4, I should be able to move from 4 back to 1, right? Within that closed system, or within that system, and then come back to my initial conditions. But then the thing about the reciprocating engine is, remember I said that we may have air and then a fuel, right? After we do our heating and our combustion and everything, we may start forming other compounds. So we now release these compounds out and then feed air and fuel back in again. So it's actually an open cycle, because it's not going to be a case like this. It's actually a point where, so it goes this way. It's either 1, 2, 3, 4, right? So this is how it actually is. It's from 1 to 2, 2 to 3, and 3 to 4. But then we don't directly move from 4 back to 1. So it's not like we just compressed, we expanded, everything was the same, and then we compressed again. We had to remove something, add something, right? So it means from 4 to 1, it goes through other processes before we bring it back to the original position. That's why it's called an open cycle, right? So it's not a true thermodynamic cycle that gets restored to its initial state, but to reduce the analysis to a manageable level, we just work with the assumption that um, it is a closed cycle, right? Okay, so I think we can just move on to the next part. So the air standard assumptions. We have what we call the air standard assumption. So these assumptions are just saying that the working fluid that we are dealing with is air, and it continuously circulates in a closed loop and behaves as an ideal gas. That's the first assumption, right? And that all the processes that make up the cycle are internally reversible. So we spoke about internal reversibility when we're looking at entropy. That's what is happening within the system can be reversed, right? Then the combustion process is replaced by a heat addition process from an external source. And then the exhaust process is replaced by a heat rejection. It's replaced by a heat rejection process, and that would restore the working fluid to its initial state. So what I'm just trying to say by these 2 points here and here is that instead of catering for the combustion of the fuel, then the removal of the exhaust gases that have gained heat, we just work with the scenarios as though we have a heat addition and a heat removal process. So remember, after we compress this gas, right? If it's a spark ignition system, we add a spark to burn it, or if it's a compression ignition system, it auto ignites, right? So it means there's going to be some kind of heat addition into the system, right? And then when we are done, the exhaust gases here would have generated some amount of heat. So what we do is that when we are pushing the exhaust gases out, they go out with that heat. So instead of us bringing in the points where we have a unit responsible for the combustion and we have a unit responsible for the removal of the exhaust gases, we just assume that we have a process, right, that is adding heat and removing heat. So that if we are drawing our cycle, instead of us placing a unit, like a whole unit for the combustion, you can just say that this is a heat addition process and then a heat removal process, and this might be our compression and then our expansion. So that's what we are just trying to say at this assumption. And I think it will make a bit more sense when we even look at the Brayton cycle more as compared to the Otto and then the diesel. Okay, so this is where our calculations are going to start from, and this is where I really need us to pay attention. Right, so the piston reciprocates in the cylinder between two fixed positions called the top dead center and then the bottom dead center. But one other important parameter is the compression ratio. So this is what we are trying to say, that if I have a piston cylinder arrangement, there's a minimum point I can bring my piston cylinder to and then the maximum point I can bring it to. Right, so if I'm trying to do an expansion, this is the lowest point I can bring my piston cylinder to. So that becomes the bottom dead center, the BDC. Then when I compress, there's a maximum point I can compress it to. I can't compress it and close the whole thing fully. So that maximum point becomes what we call the TDC. Right. Please let's mute ourselves, okay? That maximum point becomes the TDC. So what we are saying is that the volume of the maximum point, that's the BDC, divided by the volume of the minimum volume, that's the TDC, is equal to our compression ratio. So that's one thing to take note of. It becomes very important in our calculations, right? Then another important parameter is the mean effective pressure, and this is the formula for it, right? So yes, that's the formula for our mean effective pressure, right? And you can actually end up proving it because you can use it's a closed system, so change in u is equal to change in q plus w, right? And then we are saying that if you are looking at the work part, there's not going to be um, any heat that will be done. So change in q, change in u can go away. Or if you like, let's rather look at it from this perspective instead, that the w is equal to pdv. I think that's a better way to go about. So RDW is going to be equal to P dv. So if we should integrate, we can get the network here equal to P, right? Then V2 minus V1, where V2 is going to be the maximum and V1 is going to be the minimum. Then if we make P the subject, we'll have the W net over the V2 minus V1, and that will be the effective pressure, the pressure that would cause that network to be done, that net amount of work to be done. Okay, so I think we can carry on from there. Okay, so we have the ideal Otto cycle. So the Otto cycle is the ideal cycle for spark ignition reciprocating engines named after Nicholas A. Otto, and it's a four-stroke ignition cycle. So four-stroke means that it happens in four I want to look at the word. I don't want to use the word stroke again, but it happens in, let me use the word stages for now. So it looks something like this. I don't know if you can see this screen. Please, can we see the image I just projected, or how to share the screen again? Okay, okay, then that's fine. So this is how the four-stroke engine looks like, right? So we have a point where we are going to pull it down, or we are going to have, I think I can't draw on this. So we are going to have it being pulled down, and when we do, we are going to have the fluid flowing in. Then we compress, right? Then we can ignite, and then we can push out the exhaust gases. So it's going to be a four-stroke system. So it happens in four strokes. So it goes down, it comes up, it goes down, it comes up again. So that's why it's called four strokes, because it happens in four different stages or processes. Okay. Okay, so that's why it's a four-stroke system. Now, this is a more complex way of looking at it, but what we are saying is that we have a point where our exhaust gases are pushed out, right? Then our intake valve opens. When the intake valve opens, we now start to get our fluid entering through that intake valve, right? So as it enters, it means that we are expanding the system. So we are pulling down our piston. That's why the volume is increasing from the TDC to the BDC. Then we start to compress. As we compress, the volume starts to decrease again. We compress it to a point, right? And then we now ignite it. After igniting it, we can now start to um, expand it again. So now the volume starts to increase once again. Then we open the exhaust valve and then push out the exhaust gases. So that's how this cycle works. But then to have a more simplified way of looking at things, we can have this image here. And there's another one I'll show us. So what we're just trying to say is that from stage 1 to stage 2, or the first stroke, this is where we have isentropic compression, right? So remember we said that we are assuming that there are not going to be heat losses through the pipes. So the only parts where we have heat loss, the only parts where we have heat loss is when we have the heat being added, or the only parts we have heat transfer is when we have the heat being added here, or the heat being removed from here, right? So from point 1 to point 2, we have isentropic compression. We are compressing the gas. Sorry. So from point 1 to point 2, we are compressing the gas, right? So we are reducing the volume of the system. Then we can now add in our heat either by using a spark, right? So this is for a spark ignition engine. So we are adding it by a spark. So we add a spark, and then that will generate some amount of heat. When that heat is generated, right, we now start to expand the system. So as we expand the system, that's isentropic expansion. And then the exhaust gases that are formed, right, we can push them out. And as we push them out, the heat would be removed, right? So we see the points where we have constant volume processes from 2 to 3, and then from 1 to 4. So there's another graph. That one works with temperature and entropy. It's a TS diagram. And I feel like that one makes it easier to understand and easier to do calculations with. And I mean, if you are actually designing a system, you'll be more concerned with the temperatures you are getting and the entropies as compared to the pressures and then the volumes of the gas. So I think the TS diagram is more efficient in that case. So this is a TS diagram here. So I would talk about this one a little before we go into the proofs. So it's the same thing, right? It's the same as this one up here. From 1 to 2, we have isentropic compression. That's why we see that the entropy is the same. So this is the entropy axis here. Entropy at that point is the same from 1 to 2. But then you know that when you compress a gas, the temperature increases. So you see the temperature increase slightly from 1 to 2, right? Okay. Now for after that, we have from 2 to 3. So 2 to 3 is where we now have the heat being added. But then that is being done at a constant volume, right? So maybe we've compressed the gas already. Then we add the spark. When we add the spark, we don't expect the volume to be increasing. We are just adding heat to the system. So the volume is constant along this path, right? Then since we are adding the heat, the temperature is going to increase from 2 to 3. This is going to be the highest temperature in the system. Take note of that, right? Now we've added the spark, we've generated the heat, the temperature has increased. We can now start to expand. As we expand, the volume will decrease. So this is an isentropic expansion. So once again, constant entropy, right? Then we can now decrease the temperature by removing heat. So as you remove the heat, remember if you are removing the heat from the gas, the entropy will drop. But we are doing this at a constant volume as well. So I think this is the graph that we can work with more for our calculation. So the way the calculations are for the Q part, where we are adding in heat, right? Well, we are saying that over there, it's just heat that is being added. There is no work that is being done. So we know that du is equal to maybe dq plus dw, right? So in the case where there is no work being done, there's no shaft work at the part where we are adding heat. The work only happens when we are doing the expansion and the compression. So where we are adding and removing heat, there is no work done, right? So I can have here du can become u2 minus u1, or let me say uf minus ui, the final minus the initial, right, to be equal to the q at that point. So my u final minus my u initial should be equal to the q at that particular location. So if I want to look at the heat coming in here, right, I was moving from 2 to 3. So it becomes u3 minus u2. So that's what we see here. And if I want to look at the heat being removed, it's from 4 to 1, right? So I'll be having my u4 minus my u1. The reason why they're not doing final minus initial here is because this one is what's coming out, right? So ideally it's supposed to be a negative answer. If you use u1 minus u4, you get a minus, and you get a negative answer for your q, and that means it is being removed. So by the mere fact that they are defining this as q out, right, we can keep it in this form instead and just say that this amount of heat is what is being removed. But it is catered for when we bring the subtraction here, when we are doing the subtraction later on. So it's not really a problem. So the long and short of this is that if you're looking at Q in, right, is U3 minus U2. If you're looking at Q out, you can use U4 minus U1. If you use U1 minus U4, you are not wrong. Those are the answer will be negative. So you report it as heat that is being removed. Okay. Now we also know that when we look at RU, right, we know that RU can be represented with a CV, or du is equal to CV dt, right? So if I have u3 minus u2, it becomes cv t3 minus t2. And if I have u4 minus u1, it becomes cv t4 minus t1. Now the network that is being done, right, is going to be the the difference in the heat that are in the system. So now let's look at that. This time we are considering the whole cycle, not just the parts where heat is added or removed. So once again, we know that du is equal to dq plus dw. In the case where it is the whole cycle, right, du goes to zero. Consider for a cycle, things like internal energy and the rest of them, enthalpy and all of those things, the change in them goes to zero. So we can say that dq is equal to minus dw, right? So our change in q here would have been m. The lower one minus the hotter one to be equal to minus dw. So we could have sent the negative over, had qh minus qc to be equal to dw. So we saw something like this from the what's it called? The thermodynamic cycles we did previously, right? So let me see, instead of qc and q, let me rather use q out minus q in to be equal to minus dw. So that dw becomes q in minus q out. I think this is better, right? So when we do this, we'll get the expression for the w net, and you can see that it is q in cvt3 minus t2 minus q out cvt4 minus t1 divided by q in, right? And we spoke about this when we spoke about the thermodynamic cycles, but we said that for the efficiency of the cycle, we are looking at what we are getting out over what we are putting in. What we are getting out is the network. What we are putting in is the heat. So we are putting in some amount of heat to generate some amount of work. So our output is the work, the W net. That's why it's the numerator. And then our input is the heat, the Q in. That's why it's the denominator. Okay. Now, aside that, or after we are done with this part here, we can simplify the expression even further. So we know that this part here, cvt3 minus t2 over cvt3 minus t2 can cancel out. So I can represent this as cvt3 minus t2 over cvt3 minus t2, right, minus cvt4 minus t1 over cvt3 minus t2. So it's the same thing. Then this and this can cancel out to give us the 1. The CV and CV can cancel out, so we end up with just T4 minus T1 over T3 minus T2 as we see here. Then we can factorize T1 out. So if I factorize T1 out, I end up with this expression. So T1 out at the numerator, and then T2 at the denominator. So I end up with this expression. Now remember when we looked at entropy, We looked at certain relations for when we have an isentropic system under different conditions, and we came up with this formula that T1 over T2 is equal to V2 over V1. Please note this is for the part where we have a constant entropy process. So this applies for these positions here between points 1 and 2 where we have a constant entropy, then between points 3 and 4 where we have a constant entropy. You can't use these relations between points 2 and 3 and then between points 1 and 4. So please, when we are dealing with this particular equation, use it for constant entropy process. So between 1 and 2 and then between 3 and 4. Don't do it for 2 and 3 and then for 1 and 4. Otherwise you make a mistake there. Right, so T1 over T2 we said would be V2 over V1 to the power K minus 1. Right, but we also know that the volume is constant from V2 to V3. So you can see that a constant volume between V2 and V3. So it means V2 is equal to V3. And the same applies for 1 and 4. So V1 is equal to V4. So I can replace V2 here with V3 and V1 here with V4. Right, and I can also relate that to T4 over T3. So it means that T1 over T2 is equal to T4 over T3. And then I can do a change of subjects here to have T4 over T1. So I bring the T1 down here and I bring the T3 up here. Should be equal to T3 over T2. So if this, which is over here, is equal to this, which is down here, right, then it means that these terms can also cancel out. So at the end of the day, I'll be left with 1 minus T1 over T2. So that's what we see over here. I think the simplification at the end of the day is this: 1 minus T1 over T2, or we can represent T1 over T2 with our volume expression. Right, now the other thing is the compression ratio. We said that is equal to, we said R is equal to our V BDC, that's the maximum volume, over our V TDC. The maximum volume occurs at the start of the process, point 1, before we start the compression, right? And then the minimum volume happens after the compression, that's point 2. So it means that our VBDC is equal to V1, but we said there's a constant volume for V1 and V4, so that's also equal to V4. And then our VTDC is going to be V2, which is also equal to V3 because it's constant volume here and here. So it means that my R is equal to V1 over V2, which is equal to V4 over V3. So that's what we see at this point here. And now we can replace the V2 over V1 here, this part here, right, with our R. So if R is equal to V1 over V2, then it means that V2 over V1 would be 1 over R. So that's why we have 1 over R in here. So for the Otto cycle, the efficiency of the cycle at the end of the day can be represented with this formula we see, right? Can be represented with this formula we see. So we'll take an example. So we have a spark ignition engine. It's proposed to have a compression ratio of 10. So let's take it bit by bit. We have a spark ignition engine. So a spark ignition engine. So once we see a spark ignition engine, can assume that's going to be an Otto cycle. For the diesel, they'll tell you that's a compression ignition engine. So you see maybe a CI engine. So once it's spark ignition, we know that we are dealing with an Otto cycle. So even before you start, you can just have a little schematic of your graph where you have 1 going to 2, 2 going to 3, 3 coming down to 4, and then 4 coming back to 1, right? And then you can just label it so that you don't get things mixed up. So we know that this is where we have Q in, this is where we have Q out, right? Over here, so normally what I would have done is I would have put C here for compression, E here for expansion, and then I would keep this in mind that 1 and 2 is constant entropy, 3 and 4 constant entropy. So now I have this settled. Now they set a compression ratio of 10. So low compression ratio V2 over V1 is equal to V3 over V4 is equal to R. So that's equal to 10. So we have that one down. A low temperature of 200. So the low temperature would occur at point 1. That's the lowest temperature. If the question says a high temperature, that's point 3. Right? So a low temperature of 200 degrees Celsius. So at point 1, I have 200 degrees Celsius at point 1. And then I have 200 kPa at point 1. Right? And then if the work output is to be 1000 kilojoule per kilogram, so I have my net work to be 1000 kilojoule per kilogram. calculate the maximum thermal efficiency, and then compare to that of the Carnot cycle, and then calculate the mean effective pressure. Now, when we see questions like this, one thing to take note of is that we have the conditions at one location, right? And since it's a cycle, we can find what happens at point 2, at point 3, and at point 4. And that would help us know what we want to do. So we know that for the Otto cycle, the efficiency was 1 minus, let me just cross check that. So 1 minus 1 over r to the power k minus 1, right? We know our r, so we can just go ahead and find that efficiency. But for the Carnot cycle, the efficiency was 1 minus Tc over Th. Tc is going to be the lowest temperature, that's at point 1. But Th is a highest temperature, that's at point 2. So it means we need to find a way of getting the temperature at point 3 to calculate this, right? So it means that we have to find T3. Now, I said that the question also said we should calculate the MEP. You know that the MEP is equal to our W net, which we have, over our VBDC, which we don't know, minus our VTDC. So it means you have to find our VBDC and our VTDC as well. So now let's take it bit by bit. How can we first start by finding? Okay, let's first find our efficiency, because I think that's what we started with. So the efficiency of the cycle, we just put in the formula. And sorry, one other thing to note, right? They didn't, if they don't mention the working fluid, note that for spark ignition systems, it's going to be an air fuel mixture. So if they don't mention it, you can just work with air, right? So we are going to use the K value for air. So that's the 1.4. So for our efficiency of the cycle, right, we can just put in the values and then we can get our efficiency of the Otto cycle. So this is for the Otto cycle. Then we now want to find T3. So before we can find T3, we need to find T2, because as I said, it's a cycle. We move from 1 to 2, and then from 2 to 3. So you can't just jump from 1 and then relate it to 3. You need to have an intermediary relation at point 2. Right, so we work with 1 and 2. And remember, 1 to 2 was isentropic, so we can use this relation here, right? And we know that V1 over V2 is equal to R. Sorry, it means I made a mistake. Yes, supposed to be V1 over V2, the bigger over the smaller. So I made a mistake there. And then this one was supposed to be V4 over V1. Sorry for that mix up. So this is supposed to be V1 over V2 and then V4 over V3, as we said earlier, right? So sorry for that mix up. So as I was saying, we have where's the cursor? So we can have T2 over T1 to be this expression, and V1 over V2 is R, right? So it means that I can just say T2 is equal to T1 R to the power K minus 1. So that's what we see over here. Mind you, if your temperatures are not in the absolute form, put them in the absolute form. So make sure that they are in Kelvin if your the temperatures were given to you in Celsius in the question. Right, so we can do this and find the value for T2. Now we can relate T2 to T3, and we know that now that we have T2, we can relate it to T3. And we know that from 2 to 3, we have heat being added. That's where heat was being added. So we can say that our Q in is equal to CV T3 minus T2. We've already proved that, right? We know the CV of A, so we are not bothered about that. We just found T2, and we are looking for T3. So it means the other thing we need is Q in, but we don't know that value yet. So we can use a different relation. So we know that our efficiency is equal to the network over our Q in. So what we can do is that we can make Q in the subject. So we can say that Q in is equal to our network over our efficiency, and then put that in here. So I can say that my network over my efficiency should be equal to CV T3 minus T2, and I can make T3 the subject. So if I should do that, I'll have my network. I think it's better if I clean the screen. If I should do that, or let me try it down here. Sorry. If I should do that, I'll have here my network over my efficiency times my CV, right, plus T2 to be equal to my T3. And that's the expression we see here. So we know the network, we know the efficiency of the cycle we calculated, we know the CV of A, and we know our T2. We can find our T3. Now that we have our T3, we can find the efficiency of the Carnot version of this system. So that's going to be 1 minus the T lower over the T higher, right? So the lower temperature was at T1, so that's the 473.15, and then the higher was at T3, if we just calculate it. So this is the value we are going to get for the efficiency of the Carnot cycle. Now, the other part is to find the mean effective pressure, and we need the VBDC and the VTDC. So we need the volume at point 1 and point 2. We're given the pressure at 1 and then the temperature at 1, right? And we know that after the compression, we know our compression ratio, so we can find the pressure at 2. We already know the temperature at 2. So what we can do is that sorry. So what we can do is that since we know our P and our T, we can use our PV is equal to RT relation and find V1 or the VBDC, the V at point 1. So V1 is going to be R T1 over P1. And we know the R, if we are dealing with air, so it's going to be the 8.314 over the molar mass of air, which I think is 28.97 or so. Let me confirm the answer with the calculator right now. Or if anyone has a calculator here, you can just check it from whatever 28.97. Yes, so that's it. Should be getting a value of about 0.287. That's what we're expecting for the R. So it's correct. Right. So our R is going to be the 8.314 over the molar mass of air. Right. And then we know our T and our P. So that's what was done over here. Sorry. That's what was done over here. Right. To find our V1. But then we also know that V1 over V2 is equal to our compression ratio, which was 10. So V1 over 10 should be equal to V2. So we can use that to find V2 as well and then do the subtraction. So when we do that, please let's mute ourselves, okay? When we do that subtraction, right, and we put all the parameters, we know the W of the cycle, we know our V1 and V2 now. We can find the mean effective pressure. So are there any questions up to this point? So let's move on to the next cycle. I'll just explain why the value we had for the Carnot efficiency was higher than what we had for the Otto cycle. Then I'll move on to the diesel cycle. I'm just hoping we can finish in the next 30 minutes so that we don't miss anything. Okay, now when we consider the Carnot cycle, all that is being said on this slide is that the reason why the Carnot cycle is more efficient than the Otto cycle is because if you look at the Otto cycle, right, from point 2 to point 3, we are adding heat. So part of the heat that is being added is being used to raise the temperature from 2 to 3. For the Carnot cycle, we add the heat at the highest temperature point. So some of the heat is not being used to raise any temperature. For the Otto cycle, when we are removing heat, we are at point 4. So part of the heat removal is used to drop the temperature. And for the Carnot cycle, we remove heat at the lowest point. So we don't have any case where we are using some of that heat to drop the temperature. So unlike with the case of the Otto cycle, the Carnot cycle isn't giving off heat to raise temperature and to drop temperature. Right, so most of that heat can be converted into useful work. But then for the Otto cycle, that heat we have to use some to increase temperature and we have to remove some to decrease temperature. That's why it's less efficient than the Carnot system. So we also have the diesel cycle. So this is also a very interesting one. Remember I mentioned earlier that we should really pay attention to the fact that fuel is injected later. Right, that's why the graph here looks a little bit different. So I'll explain what is happening on this graph. So what's happening is that from point 1 to point 2 is almost the same as the Otto system. We have an isentropic compression. So we are compressing our gas. That's why the volume is reducing. But after we compress the gas, right, we have a certain volume it has gotten to the minimum volume, right? So that's the VTDC. And then we now start to inject the fuel into it. So now that we are injecting the fuel into it, the volume will increase slightly because we are adding some fuel into it. So now it increases to V3, right? Then we now do our burning. So it now ignites, it combusts, and then we can now do our isentropic expansion, right? And then we can remove the heat. So it's almost the same thing. The only difference is the difference from point 2 to point 3. So one thing to note, when we have our V1 over our V2, that was our compression ratio. And now we have a new relation as well, and that is going to be our, I think it's V3 over V2. And that's going to be what we call the cut-off ratio. Cut-off ratio because it's the point at which we stop adding fuel. So we cut off the flow of fuel. Right, so that volume is dependent on how much fuel we are adding. If I add fuel to a certain degree, I'll increase the volume to a certain degree. The moment I stop adding fuel, then that becomes the cut-off ratio. So for the diesel cycle, if we are looking at it in terms of temperature and entropy, from point 1 to point 2, we have our isentropic compression, right? Then we are keeping the pressure constant and we are adding in our fuel. So we are doing this as a constant pressure process. And when we do that, it auto ignites and then we have the heat being added here, right? Then we can now do our isentropic expansion and then we can remove our heat at constant volume to come back to point 1. So realize that for this case here, we are now dealing with enthalpy, right, instead of internal energy, because the fuel that is coming in, we are doing this by injecting the fuel in. So the fuel is flowing in. Since the fuel is going to flow, it is no longer going to be considered as a closed cycle for that part. That's why we are working with enthalpy here. Right, so we have here H3 minus H2 for the Q in part, and then for the Q out part is U4 minus U1, right? So that's for the Q out, and it's going to be this a very similar process as to what we've done previously. So our network is going to be our Q in minus our Q out, so that's the top part here, and then we have the denominator to be Q in. We can simplify that what we did previously and end up with this. Now this part that is coming in here, remember we said that we have this relation, right? So if I should divide through by CV, right? If I should, let me do it this way. If I should divide everything through by CV, what we are going to get is we'll have CP over CV, T3 minus T2 minus CV over CV, T4 minus T1, all over CP over CV, T3 minus T2, right? So then this can give us our K, and then this can go away to 1. So we end up with K T3 minus T2 minus T4 minus T1 all over K T3 minus T2. And just as we did previously, let me clear this part. Just as we did previously, we can write this as K T3 minus T2 over K T3 minus T2, right, minus T4 minus T1 over K T3 minus T2. So this cancels out to give us the 1 here, and then this part that is left here is what we see over here. And just as we did, we factorize T1 and T2 out. We can factorize T1 and T2 out so that we have the expression in this way. Then let me clean this part first. Okay, so we can factorize T1 and T2 out to have an expression in this way. Then using the expressions we did when we're looking at entropy, we have this expression here as well, right? So we can just work with these ones. We also have a cutoff ratio, the V3 over V2 over here. I remember we said that V1 is going to be equal to V4. That part is going to be a constant volume process. So from V1 is going to be equal to V4. So we can just do a change of subject with all these things, right? And then end up with this expression here for our T3. So this part is just algebra, just change of subject, right? So we can carry on with all of that, and then we end up with this final relation down here. Now when we do that, we realize that it's very similar to what we did for the Otto cycle. So for the Otto cycle we had this, but then for the diesel cycle we are having this part attached to it. And since this is always going to be greater than 1, if it's added to it, it means that the efficiency overall would be less. So if you look at it, I have maybe 1 minus a certain value, right? This is going to give me another value. And then if I should have another term, a term that is greater than 1 multiplying this, let's say 2, right, I'll end up having this being reduced because I'm subtracting a bigger number from 1. So the efficiency at the end of the day will reduce, right? So that's why we have efficiency of a diesel cycle to be less than that of an Otto cycle. And then the only advantage is that when we use a diesel cycle, the compression ratio can be much higher without the possibility of a pre-combustion ignition. So we don't have a case where before it starts to burn before we want it to burn. So we have this example here. So it's an ideal diesel cycle with air as the working fluid, has a compression ratio of 18 and then a cutoff ratio of 2. At the beginning of the compression process, the working fluid is at 101.32 kPa, 25 degrees Celsius, and then 1917 centimeter cube. Utilizing the code as standard assumptions, let's determine the temperature and pressure of air at the end of each process, and then the network output and thermal efficiency, and then the mean effective pressure. So we know compression ratio to be 18 and our cutoff ratio to be 2. We also know the K of air, we know our P1 and we know our T1, right? So if we should use the um, diagram that was with temperature and enthalpy, we would have this. So this is enthalpy and this is temperature. So we have from 1 to 2, 2 to 3, and then 3 back to 4. So we know that at this point, if we are doing our compression, at this point here, we are going to have our heat being added, right? And then this is at a constant pressure. Here we are going to have our expansion being done, and then here we have our heat being removed. So this is our Q out, and then this side is at constant volume, right? And we know that from 1 to 2, since it's going to be isentropic, we can use those relations. So we have the relation we derived earlier, put in our value of our R and get our value at T2, right? And then we can also do the same thing with P, because the relations were for, I think I've opened that one here, right? So these relations here, so we can also relate it to pressure as well. So we can do it with these relations as well. So if we do that, we can end up with these expressions, right? And then we can find the P2 as well. So between 1 and 2, we can just use the isentropic expressions relating temperature and volume, or temperature and pressure, or volume and temperature, or volume and pressure, right? So that we can find the other. Then from T3 to T2, we said we can represent it with RC T2, the compression ratio times T2. So we can use that to find, sorry, the cutoff ratio. We can use that to find RT3, right? And then from there we can find the pressure at that point with the same expression. Then we also know from 4 to 3 or 3 to 4 is going to be isentropic again, so we can work with those same relations, right? But remember, between 1 and 4, the volume is the same, so I can use these relations to find the volume at point 2, right? Or in fact, sorry, at point 2 we can use the compression ratio, because you know that V1 over V2 is equal to our R. So we can find the volume at point 2, and then at point 3 we know that our V3 over V2 is going to be our RC, so we can use that to find the volume at point 3 as well. So by doing this, we can find the temperature at all the locations, find the volumes at all the locations, and then equally find the pressures at all the locations. Especially when we know temperature and then volume, we can easily find our pressures as well, or we can end up using these relations to find our pressures. Then we just put in the values we've gotten into the expression to get the efficiency of the cycle. And then to get the network, we also once again already have all these values, so we can find the network, right? We know our CP, we know our CV, we now know our T3, T2, T4, and T1, so we can find the network that will be done. Okay, I think this is the one we just solved. Okay, so this is another example. So this one says that a diesel cycle, okay, I think because of time, you guys can try this one out. The solution is there, right? But then it works on, it's a very similar question to what we did for the Otto cycle, just at this time it's working with a diesel cycle. So you either use the equations for a diesel cycle instead of the Otto cycle, and then you can just confirm your answer. It's actually a very similar format, just at this time we are working with it as a diesel cycle. So use a diesel cycle equations and do that. The only issue might come in at this point here. So remember that we have the efficiency to be equal to the W over the Q. So we can make Q to be equal to W over the efficiency, right? And then for the W is going to be Q in minus Q out, right? So we know that W is Q in minus Q out, so that's this minus this, right? And then they just found an expression relating T4 to T3 using the isentropic relations. So that's what they've done here, right? And they give the W, so you know that your W is equal to this minus this. So you can just play around with those values. You can get your CP and everything, change T4 to T3, make T3 the subject, and you get this value. Then from there you can use it to find T4, right? So the beginning is almost similar to what we did for the Otto cycle. The only problem comes in here. So just know that your W is your Q in minus Q out, right? So you can have the expressions for that, and then you can relate your T4 and your T. I think there's a question. Okay, someone says I should go over this part. Okay, I wanted to beat time, but let me take it one by one. So what I'm trying to say is, When we it's a similar question to what we did for the Otto cycle, just that this time we want to apply it to the diesel cycle, right? So we know the efficiency of the diesel cycle is given by this, right? And the question gave us our compression ratio, but we don't know our cutoff ratio, so we need to find that before we can solve for our efficiency. We know the pressure at point 1, the temperature at point 1, right? So we can now find what's happening at point 2. So remember, our system is like this: 1, 2, 3, 4. 1 to 2 is isentropic, so we can use those relations, right, to find the pressure. We can relate pressure and volume using the isentropic relations to find the pressure, because from the question we know um, our V1 over V2 will be equal to our R. So I can just get this to become the R. So I can release the pressure to that expression and find my P2. I can do the same thing with the temperature at point 2 with the isentropic expressions and find my T2, right? Then now I want to find T3 because I need to find V3 and I need to find V2 before I can find my RC. Yes, I need V3 and V2 before I can find my RC, and I need the RC to find my efficiency, right? So it means that now I need a relation to get me my T3. So if I work with the I remember, unlike in the first is that we could have just done CP T 3 minus T2. We can't just go ahead and do that now, right? So what we can rather do is that we can, but the reason, let me explain why we can't do that. The reason why we can't do that is because over here we have heat being added. So we could have said that fine, the heat being added is equal to Cp T3 minus T2, but we don't know the heat being added, so we can't use that expression. So what we rather do is that we use what we know. The question gave us the work, right? So we work with the work instead. So we know that the work is Q in minus Q out. So that's going to be the Cp T3 minus T2 minus Cv T4 minus T1. That should be equal to the work. But now we have a number of unknowns. So now let's look at it. From the work expression, we found T2, we found T1. We know Cv, we know Cp, and we know the W net. So what we don't know is T3 and T4. But T3 and T4 are on an isentropic path, right? So we can relate them with the isentropic relations. So I can use the isentropic relations to relate T3 and T4. So we are using this part here, that T4 over T3 is equal to V3 over V4 the power K minus 1, right? But once again, we don't know, or once again, the constant volume is here, so we know that V1 is equal to V4, right? So yes, V1 is equal to V4, but then we don't know V3 yet. So we can even get an expression for V4, but we still don't know V3. So that's why they brought in this expression now to relate V3 and T3. So they did T3 over T2 to be equal to V3 over V2, so that they can now make V3 the subject, which we don't know, right? When we do that, we get this, and I can put that in here to replace V3. So V3 now becomes the V2 T3 over T2, and then the V4 now becomes V1 down here, so that I can relate T4 and T3 to T3 and T2. So I just want to keep all my unknowns as minimal as possible. That's what we are just trying to do. We are keeping all our unknowns as small as possible. So if I have a relation that has other parameters and my unknowns are T3 and T4, I'll keep trying to relate everything to that T3 and T4, right? So that's what we are just trying to do by that. So from that point there, we can find our V2 because we know our T2 and P2. So we can use the ideal gas equation, find our V2, right? So we can find our V1 as well using that same ideal gas equation because we know T1 and P1, right? So now we know V2, V1 from this part up here, right? So the only unknown now is T3 and still T4. So we can relate T4 and T3, and then we get this. So T4 is going to be equal to this. Then we come back to the work expression we found, and then we can put the expression for T4 in there. So remember that this side was T4 minus T, was it T, it was T4 minus T1, yeah, right? So minus T1, so we can replace the T4 here with the expression for T4 here, right? So that's what we have over here. And then we can just make T3 the subject now because now it's only going to be T3, that is our unknown. So when we do that, T3 becomes this. We can use that to find T4 and we are done. Now that we know T3 and we know T4, we can also now find V3 because we said earlier that V3 was equal to V2 times T3 over T2. Now that we know T3, we can find V3. And if we know V3, we can find our compression ratio. That's V3 over V2. Okay, I think my time is almost up. Okay, let me try and be fast about this. A minute here. Okay, so let's try and finish up with this. So that will give us the value for our compression ratio. Then the efficiency for the diesel cycle, we already have the formula, so we put in the values and we can compare it to the Otto cycle expression. Then for the mean effective pressure, we already know our VBDC, that's V1, and we know our VTDC, that's V2, so we can put in the expressions and then get our final answer. So the last cycle we have to do is the Brayton cycle, right? So for the sake of time, I would go straight to the image and then use that to explain what happens with the Brayton cycle, give a few points, and then I think I'll try and finish solving the question on time. Just a minute. Let's try and finish up. So for the Brayton cycle, right, we have these processes. So we have a case where we start with our fluid, we compress it, right? And when we compress it, so okay, I'll mention this when we are done. When we compress it, the temperature would increase a bit, right? So we have T1, we have T2. Then we send it through a point where we add heat. So this side becomes T3. Then we expand it through a turbine to generate our amount of work. When we expand it, the temperature drops to T4. Then, okay, so from T4, right, we remove the remaining heat to bring it back to T1. Now, remember we mentioned earlier that we are going to assume that there are no friction losses and pressure drops, right? So it means that if I compress, this is P1. If I compress, it gets to P2. While it moves from 2 to 3, there's no pressure drop. So at point 3, the pressure is the same as P2, right? Then when I come down to 4, I've expanded. The pressure will be the same as what enters the compressor. So this is also at P1. So please take note of that, right? That's something I really need us to take note of. So what I'm trying to say is that for the Brayton cycle, okay, I think I'll mention this as well. I almost forgot. So for the Brayton cycle, we have here T1, T2, T3, and T4. Then we have P1, we have P2, we have P3, we have P4. But P1 is equal to P4 and P2 is equal to P3. Now the expansion and the compressions are going to be done isentropically. So we can use the isentropic relations for our T, our P, and our V at those points as well. I think there's a question. Someone is asking why. Please, why to? What's in particular? Is it why the pressure isn't dropping? Or you can unmute and ask the question. Why P1 is equal to P4? Okay, so what I was saying was that we are going to, okay, let me do it this way. So whatever is leaving the turbine, right, is leaving at a certain pressure. That's P4, right? And what happens is that it's going to move through this heat exchanger, but the pressure is not going to drop. And then it comes back to this point. So imagine that this side is at P4, right? It moves to another unit, nothing happens to the pressure, and it comes back here. So it means that before it enters the compressor, it will also be at that same pressure. So that's why P1 is equal to P4. And the reason why P2 is equal to, oh sorry, the reason why P2 is equal to P3 is because the same understanding. After we've compressed, the pressure increases, right? So after we compress it in the, or after we pass it through the compressor, the pressure would increase to P2. But from P2, after it has been increased here, it passes through a heat exchanger. Nothing happens to the pressure because we said we are assuming there are no pressure drops. Right, so it passes through the heat exchanger, there's nothing happening to the pressure. Then it comes back out. Right, so whatever has entered and come out is going to be at that same pressure. That's why P1 and P4 are the same, and then P2 and P3 are the same. I hope it makes sense. Okay, so for the Brayton cycle, that's it, right? And then the efficiency, remember that normally our efficiency was our network over our kill in. Now our network is going to be the work that the turbine does minus the work that we put in because of the compressor, right? So we put in some work to do the compression, and then from the turbine we generate some work, right? So the net work is going to be what we are getting out minus what we put in, divided by our Q in, which we know to be CP T3 minus T2. So the reason why it is T3 minus T2 is because this is where Q in is being done, right? And since it's going to be an open system, we have here CP T3, that's what's coming out here, minus T2, what's coming in there. So that's for the Q in, right? Then for the we can simplify it further. So just like what we did previously, we can divide Cp of air by Cp of air and all of those things, rearrange our expressions, right? And then we end up with this formula for the efficiency of our cycle, right? So we can just expand what we have up here. So let me do it so that no one becomes confused. How do I reduce this? Okay, so what we can do is, once again, these things are just algebra, so I really wanted to focus more on the final forms. But what's happening is we can say Cp T3 minus Cp T4 minus Cp T2 plus Cp T1. Then we can just make Cp T3 minus T2, right? Then plus Cp, or let's say minus Cp rather. So we first expand and then we group. So minus Cp T is T4, yes, T4 minus T1, right? So now we have CP T3 minus T2. If we use a similar approach to what we did previously, that can also come and cancel what is down here. And then it leaves us with this expression. Then we can factorize T1 and T2 out, then use our isentropic relations, right? And then get these expressions, right? Then just as we did for the Otto cycle, we can simplify it all the way and end up with this for the efficiency of our cycle. Is that okay? So we have an example here. I think this is the last thing I'll do before our time runs out. I think this one, the solution wasn't there, so I'll do more writing. So the question says that we have a gas turbine power plant operating on an ideal Brayton cycle, and it has a high pressure ratio of 8. The gas temperature is 300 Kelvin at the compressor inlet and 1300 Kelvin at the turbine inlet. Utilizing the air standard assumptions, we should determine the gas temperature at the exit of the compressor and the turbine, and then the back work ratio, and then the thermal efficiency. So let's first start with a diagram. So we can have our Brayton cycle. So we have a compressor. Sorry, it's difficult to draw with this. So we have here a compressor. We have here a heat addition section. We have a turbine. Then we have a heat removal section. And then we can bring it back. So we have here point 1, point 2, point 3, point 4. Now the question told us, or let me write everything. So this side we had 300 Kelvin for T1. What's entering the compressor? Compressor inlet 300, and then turbine inlet, that's T3, right? So this side is at 1300 Kelvin. So we have it moving this way, right? And then we have here Q in, and then we have here Q out. Now the question told us that we have a pressure ratio. Realize that this time is not a compression ratio. Compression ratio, we used volume, right? V1 over V2. Pressure ratio, we are using pressure, so the higher pressure over the lower pressure, right? So that's going to be our pressure ratio. So we can say that our P2 over P1 is equal to 8. Okay, now we want to find the temperature at the exit of the compressor. So we're interested in T2. We know T1 and T3, and then we are also interested in the temperature at the exit of the turbine, that's T4. But remember we said from 1 to 2 is isentropic, so we can use the isentropic relations. So T2 over T1 is equal to P2 over P1, right? So the power K minus 1 over K. But P2 over P1 we said is 8. So I can replace that. And say that my T2 over T1 is equal to 8 to the power, our K is 1.4, right? So 1.4 minus 1 over 1.4. Then I can say T2 is equal to, T1 was 300 Kelvin, so 300 times 8 to the power 0.4 over 1.4. When we compute this, we should be getting a value of 543.43. So you can confirm the answers later. So I had 543.43. Can punch it in the calculator and confirm. So this should be 543.43 Kelvin for T2. And then between T3 and T4, it's also going to be isentropic. So I can say that T4 on T3 should be equal to P4 on P3, right, to the power K minus 1 over K. But we said that P2 was equal to P3 and P1 was equal to P4. So if I'm having P4 over P3 is the inverse of the compression ratio. So it means that this is going to be 1 over 8. So T4 over T3 is equal to 1 over 8 K minus 1 over K. We know T3 to be 1300. So let me write it up here. So I can have 1300 1 over 8 to the power K minus 1 over K. And when I should do this and compute it, I should be getting T4. The screen is really messy. I should be getting T4 to be about 717.66 Kelvin. So that will be the outlet temperature. So all we are just trying to say is that you can draw your diagram first, right? And since T1 and T2 are isentropic, you can use that relation, work with your pressure ratio, and then get your temperature for T2. Then you can do the same thing between T3 and T4. Write the isentropic relation, work with your pressure ratio, right, and then get the value for T4. So I'll clear this and then I'll do the calculation for the back work ratio. So you can confirm the answers that I had when I did the calculation later when you try it on your own. So for that one, I had T2 to be 543.43 Kelvin, and then I had T4 to be 717.66 Kelvin. Okay, then the back work ratio. Back work ratio is just looking at the work that is done by the compressor divided by the work done by the turbine. The work done by the compressor is going to be H2. I think I have to do the diagram again. So this is our compressor and this is our turbine. Just for those parts, this is 1, 2, 3, 4. What's being done by the compressor? Sorry, I think I'm getting. Okay, so sorry about that. So the compression ratio is the work of the compressor over that of the turbine. And for the compressor, we know that since it's going to be a flow work, it will be H2 minus H1. For the turbine, right, we would have it to be H3 minus H4. So we are just using the higher ones minus the lower ones. But then we can represent this as Cp T2 minus T1 over Cp T3 minus T4. So the Cp can cancel out. And then we just put in the values we had for T2, T1, T3, and T4. So if we do that, we should get a value of about 0.42 for the back work ratio. And then for the thermal efficiency, it was 1 minus T1 over T2, right? So that's going to be 1 minus T1 over the T2 we had. And then the answer I had was 0.448 for our efficiency, right? So you can try them out. Once again, if you have any issues, you can just reach out to me later. So that's it for the gas cycle, right? We'll move on to vapor cycles the next time. So I think that will be on Friday, and we should be done with thermodynamics. So the subsequent week, we'll just be solving as many questions as possible. Okay, so before I officially end everything, is there any question, or is there anything anyone would want to say? Is there any question? Sorry I had to rush through at the end there. I have to be in another meeting, so. But if there are any issues, you can reach out to me later, and I'll still address the issues for you.